Author's preface to the first edition. Popular lectures, owing to the knowledge they presuppose and the time they occupy, can afford only a modicum of instruction. They must select for this purpose easy subjects and restrict themselves to the exposition of the simplest and the most essential points. Nevertheless, by an appropriate choice of the matter, the charm and the poetry of research can be conveyed by them. It is only necessary to set forth the attractive and the alluring features of a problem, and to show what broad domains of fact can be illuminated by the light radiating from the solution of a single and oft-times unobtrusive point. Furthermore, such lectures can exercise a favorable influence by showing the substantial sameness of scientific and everyday thought. The public, in this way, loses its shyness towards scientific questions and acquires an interest in scientific work, which is a great help to the inquirer. The latter, in his turn, is brought to understand that his work is a small part only of the universal process of life, and that the results of his labours must redound to the benefit not only of himself and a few of his associates, but to that of the collective whole. I sincerely hope that these lectures, in the present excellent translation, will be productive of good in the direction indicated. Ernst Mach Prague, December 1894. The Forms of Liquids. What thinkest thou, dear Euthyphron, that the holy is, and the just, and the good? Is the holy holy because the gods love it, or are the gods holy because they love the holy? By such easy questions did the wise Socrates make the marketplace of Athens unsafe and relieve presumptuous young statesmen of the burden of imaginary knowledge, by showing them how confused, unclear, and self-contradictory their ideas were. You know the fate of the importunate questioner. So-called good society avoided him on the promenade. Only the ignorant accompanied him. And finally, he drank the cup of hemlock, a lot which we oft-times wish would fall to modern critics of his stamp. What we have learned from Socrates, however, our inheritance from him, is scientific criticism. Everyone who busies himself with science recognizes how unsettled and indefinite the notions are which he has brought with him from common life, and how, on a minute examination of things, old differences are effaced and new ones introduced. The history of science is full of examples of this constant change, development, and clarification of ideas. But we will not linger by this general consideration of the fluctuating character of ideas, which becomes a source of real uncomfortableness when we reflect that it applies to almost every notion of life. Rather shall we observe by the study of a physical example how much a thing changes when it is closely examined, and how it assumes, when thus considered, increasing definiteness of form. The majority of you think, perhaps, you know quite well the distinction between a liquid and a solid, and precisely persons who have never busied themselves with physics will consider this question one of the easiest that can be put. But the physicist knows that it is one of the most difficult. I shall mention here only the experiments of Tresca, which show that solids subjected to high pressures behave exactly as liquids do. For example, may be made to flow out in the form of jets from orifices in the bottoms of vessels. The supposed difference of kind between liquids and solids is thus shown to be a mere difference of degree. The common inference that because the earth is oblate in form, it was originally fluid, is an error in the light of these facts. True, a rotating sphere, a few inches in diameter, will assume an oblate form only if it is very soft, for example, is composed of freshly kneaded clay or some viscous stuff. But the earth, even if it consisted of the rigidest stone, could not help being crushed by its tremendous weight, and must perforce behave as a fluid. Even our mountains could not extend beyond a certain height without crumbling. The earth may once have been fluid, but this by no means follows from its oblateness. The particles of a liquid are displaced on the application of the slightest pressure. A liquid conforms exactly to the shapes of the vessels in which it is contained. It possesses no form of its own, as you have all learned in the schools, accommodating itself in the most trifling respects to the conditions of the vessel in which it is placed, and showing, even on its surface, where one would suppose it had the freest play, nothing but a polished, smiling, expressionless countenance. It is the courtier par excellence of the natural bodies, liquids have no form of their own. No, not for the superficial observer. But persons who have observed that a raindrop is round and never angular will not be disposed to accept this dogma so unconditionally. It is fair to suppose that every man, even the weakest, would possess a character, if it were not too difficult in this world to keep it. So too, we must suppose that liquids would possess forms of their own, if the pressure of the circumstances permitted it, if they were not crushed by their own weights. An astronomer once calculated that human beings could not exist on the sun, apart from its great heat, because they would be crushed to pieces there by their own weight. The greater mass of this body would also make the weight of the human body there much greater. But on the moon, because here we should be much lighter, we could jump as high as the church steeples without any difficulty, with the same muscular power which we now possess. Statues and plaster casts of syrup are undoubtedly things of fancy, even on the moon. But maple syrup would flow so slowly there that we could easily build a maple syrup man on the moon, for the fun of the thing, just as our children here build snowmen. Accordingly, if liquids have no form of their own with us on Earth, they have perhaps a form of their own on the moon, or on some smaller and lighter heavenly body. The problem, then, simply is to get rid of the effects of gravity, and this done, we shall be able to find out what the peculiar forms of liquids are. The problem was solved by Plato of Ghent, whose method was to immerse the liquid in another of the same specific gravity. He employed for his experiments oil and a mixture of alcohol and water. By Archimedes' well-known principle, the oil in this mixture loses its entire weight. It no longer sinks beneath its weight. Its formative forces, be they ever so weak, are now in full play. As a fact, we now see, to our surprise, that the oil, instead of spreading out into a layer, or lying in a formless mass, assumes the shape of a beautiful and perfect sphere, freely suspended in the mixture, as the moon is in space. We can construct in this way a sphere of oil several inches in diameter. If, now, we affix a thin plate to a wire and insert the plate in the oil sphere, we can, by twisting the wire between our fingers, set the whole ball in rotation. Doing this, the ball assumes an oblate shape, and we can, if we are skillful enough, separate by such rotation a ring from the ball, like that which surrounds Saturn. This ring is finally rent asunder, and, breaking up into a number of smaller balls, exhibits to us a kind of model of the origin of the planetary system, according to the hypothesis of Kant and Laplace. Still more curious are the phenomena exhibited when the formative forces of the liquid are partly disturbed by putting in contact with the liquid's surface some rigid body. If we immerse, for example, the wire framework of a cube in our mass of oil, the oil will everywhere stick to the wire framework. If the quantity of oil is exactly sufficient, we shall obtain an oil cube with perfectly smooth walls. If there is too much or too little oil, the walls of the cube will bulge out or cave in. In this manner, we can produce all kinds of geometrical figures of oil, for example, a three-sided pyramid, a cylinder, by bringing the oil between two wire rings, and so on. Interesting is the change of form that occurs when we gradually suck out the oil by means of a glass tube from the cube or pyramid. The wire holds the oil fast. The figure grows smaller and smaller until it is at last quite thin. Ultimately, it consists simply of a number of thin, smooth plates of oil, which extend from the edges of the cube to the center, where they meet in a small drop. The same is true of the pyramid. The idea now suggests itself that liquid figures as thin as this, and possessing, therefore, so slight a weight, cannot be crushed or deformed by their weight. Just as a small, soft ball of clay is not affected in this respect by its weight. This being the case, we no longer need our mixture of alcohol and water for the production of figures, but can construct them in the open air. And Plato, in fact, found that these thin figures, or at least very similar ones, could be produced in the air by dipping the wire nets described in a solution of soap and water and quickly drawing them out again. The experiment is not difficult. The figure is formed of itself. The preceding drawing represents to the eye the forms obtained with cubical and pyramidal nets. In the cube, thin, smooth films of soapsuds proceed from the edges to a small quadratic film in the center. In the pyramid, a film proceeds from each edge to the center. These figures are so beautiful that they hardly admit of appropriate description. Their great regularity and geometrical exactness evokes surprise from all who see them for the first time. Unfortunately, they are of only short duration. They burst on the drying of the solution in the air, but only after exhibiting to us the most brilliant play of colors, such as is often seen in soap bubbles. Partly their beauty of form, and partly our desire to examine them more minutely, induces us to conceive of methods of endowing them with permanent form. This is very simply done. Instead of dipping the wire nets in solutions of soap, we dip them in pure melted colophonium, resin. When drawn out, the figure at once forms and solidifies by contact with the air. It is to be remarked that also solid fluid figures can be constructed in the open air if their weight be light enough, or the wire nets of very small dimensions. If we make, for example, of very fine wire a cubical net whose sides measure about 1/8 of an inch in length, we need simply to dip this net in water to obtain a small solid cube of water. With a piece of blotting paper, the superfluous water may be easily removed and the sides of the cube made smooth. Yet another simple method may be devised for observing these figures. A drop of water on a greased glass plate will not run if it is small enough, but will be flattened by its weight, which presses it against its support. The smaller the drop, the less the flattening. The smaller the drop, the nearer it approaches the form of a sphere. On the other hand, a drop suspended from a stick is elongated by its weight. The undermost parts of a drop of water on a support are pressed against the support, and the upper parts are pressed against the lower parts because the latter cannot yield. But when a drop falls freely downward, all its parts move equally fast. No part is impeded by another. No part presses against another. A freely falling drop, accordingly, is not affected by its weight. It acts as if it were weightless. It assumes a spherical form. A moment's glance at the soap film figures produced by our various wire models reveals to us a great multiplicity of form. But great as this multiplicity is, the common features of the figures also are easily discernible. All forms of nature are allied, though none is the same as the other. Thus, their common chorus points to a hidden law. This hidden law Plato discovered. It may be expressed, somewhat prosily, as follows. 1. If several plane liquid films meet in a figure, they are always 3 in number, and, taken in pairs, form, each with another, nearly equal angles. 2. If several liquid edges meet in a figure, they are always 4 in number, and, taken in pairs, form, each with another, nearly equal angles. This is a strange law, and its reason is not evident, but we might apply this criticism to almost all laws. It is not always that the motives of a lawmaker are discernible in the form of the law he constructs. But our law admits of analysis into very simple elements or reasons. If we closely examine the paragraphs which state it, we shall find that their meaning is simply this, that the surface of the liquid assumes the shape of smallest area that is possible under the circumstances. If, therefore, some extraordinarily intelligent tailor, possessing a knowledge of all the artifices of the higher mathematics, should set himself the task of so covering the wire frame of a cube with cloth that every piece of cloth should be connected with the wire and joined with the remaining cloth, and should seek to accomplish this feat with the greatest saving of material, he would construct no other figure than that which is here formed on the wire frame in our solution of soap and water. Nature acts in the construction of liquid figures on the principle of a covetous tailor, and gives no thought in her work to the fashions. But, strange to say, in this work, the most beautiful fashions are of themselves produced. The 2 paragraphs which state our law apply primarily only to soap film figures, and are not applicable, of course, to solid oil figures. But the principle that the superficial area of the liquid shall be the least possible under the circumstances is applicable to all fluid figures. He who understands not only the letter, but also the reason of the law, will not be at a loss when confronted with cases to which the letter does not accurately apply. And this is the case with the principle of least superficial area. It is a sure guide for us even in cases in which the above-stated paragraphs are not applicable. Our first task will now be to show by a palpable illustration the mode of formation of liquid figures by the principle of least superficial area. The oil on the wire pyramid in our mixture of alcohol and water, being unable to leave the wire edges, clings to them, and the given mass of oil strives so to shape itself that its surface shall have the least possible area. Suppose we attempt to imitate this phenomenon. We take a wire pyramid, draw over it a stout film of rubber, and in place of the wire handle, insert a small tube leading into the interior of the space enclosed by the rubber. Through this tube, we can blow in or suck out air. The quantity of air in the enclosure represents the quantity of oil. The stretched rubber film, which, clinging to the wire edges, does its utmost to contract, represents the surface of the oil endeavoring to decrease its area. By blowing in and drawing out the air, now, we actually obtain all the oil pyramidal figures, from those bulged out to those hollowed in. Finally, when all the air is pumped or sucked out, the soap film figure is exhibited. The rubber films strike together, assume the form of planes, and meet at 4 sharp edges in the center of the pyramid. The tendency of soap films to assume smaller forms may be directly demonstrated by a method of van der Mensbrugge. If we dip a square wire frame to which a handle is attached into a solution of soap and water, we shall obtain on the frame a beautiful plain film of soap suds. On this we lay a thread having its 2 ends tied together. If now we puncture the part enclosed by the thread, we shall obtain a soap film having a circular hole in it, whose circumference is the thread. The remainder of the film decreasing in area as much as it can, the whole assumes the largest area that it can. But the figure of largest area, with a given periphery, is the circle. Similarly, by the principle of least superficial area, a freely suspended mass of oil assumes the shape of a sphere. The sphere is the form of least surface for a given content. This is evident. The more we put into a traveling bag, the nearer its shape approaches the spherical form. The connection of the 2 above-mentioned paragraphs with the principle of least superficial area may be shown by a yet simpler example. Picture to yourselves 4 fixed pulleys, I, B, C, D, and 2 movable rings, G. About the pulleys, and through the rings, imagine a smooth cord passed, fastened at one extremity to a nail, and loaded at the other with a weight. Now this weight always tends to sink, or, what is the same thing, always tends to make the portion of the string EH as long as possible, and consequently, the remainder of the string, wound round the pulleys, as short as possible. The strings must remain connected with the pulleys, and on account of the rings also with each other. The conditions of the case, accordingly, are similar to those of the liquid figures discussed. The result also is a similar one. When, as in the right-hand figure of the cut, 4 pairs of strings meet, a different configuration must be established. The consequence of the endeavor of the string to shorten itself is that the rings separate from each other, and that now at all points only 3 pairs of strings meet, every 2 at equal angles of 120 degrees. As a fact, by this arrangement, the greatest possible shortening of the string is attained, as can be easily proved by geometry. This will help us to some extent to understand the creation of beautiful and complicated figures by the simple tendency of liquids to assume surfaces of least superficial area. But the question arises, why do liquids seek surfaces of least superficial area? The particles of a liquid cling together. Drops brought into contact coalesce. We can say, liquid particles attract each other. If so, they seek to come as close as they can to each other. The particles at the surface will endeavor to penetrate as far as they can into the interior. This process will not stop, cannot stop, until the surface has become as small as under the circumstances it possibly can become, until as few particles as possible remain at the surface, until as many particles as possible have penetrated into the interior, until the forces of attraction have no more work to perform. The root of the principle of least surface is to be sought, accordingly, in another and much simpler principle, which may be illustrated by some such analogy as this. we can conceive of the natural forces of attraction and repulsion as purposes or intentions of nature. As a matter of fact, that interior pressure which we feel before an act and which we call an intention or purpose is not, in a final analysis, so essentially different from the pressure of a stone on its support or the pressure of a magnet on another that it is necessarily unallowable to use for both the same term, at least for well-defined purposes. It is the purpose of nature, accordingly, to bring the iron nearer the magnet, the stone nearer the center of the earth, and so forth. If such a purpose can be realized, it is carried out. But where she cannot realize her purposes, nature does nothing. In this respect, she acts exactly as a good man of business does. It is a constant purpose of nature to bring weights lower. We can raise a weight by causing another, larger weight to sink. That is, by satisfying another, more powerful, purpose of nature. If we fancy we are making nature serve our purposes in this, it will be found, upon closer examination, that the contrary is true, and that nature has employed us to attain her purposes. Equilibrium, rest, exists only, but then always when nature is brought to a halt in her purposes, when the forces of nature are as fully satisfied as, under the circumstances, they can be. Thus, for example, heavy bodies are in equilibrium when their so-called center of gravity lies as low as it possibly can, or when as much weight as the circumstances admit of has sunk as low as it can. The idea forcibly suggests itself that perhaps this principle also holds good in other realms. Equilibrium exists also in the state when the purposes of the parties are as fully satisfied as for the time being they can be, or, as we may say, jestingly, in the language of physics, when the social potential is a maximum. You see, our miserly mercantile principle is replete with consequences. The result of sober research, it has become as fruitful for physics as the dry questions of Socrates for science generally. If the principle seems to lack in ideality, the more ideal are the fruits which it bears. But why, tell me, should science be ashamed of such a principle? Is science itself anything more than a business? Is not its task to acquire with the least possible work, in the least possible time, with the least possible thought, the greatest possible part of eternal truth?